Hello and welcome to our final chapter, chapter 12. We are going to be working with solids this chapter. We're going to be working with volume and surface area. So kind of like last chapter, but we're moving on to three-dimensional shapes. In this section here, there's just a ton of vocab. And so it's just going to be notes and practicing some of that vocab. There's really not a lot of math. There's one formula in it, but it's not even what you'd think. So let's start with what a polyhedron is. It's a solid that's bounded by polygons. So we're going to basically be taking a bunch of polygons together and creating some shapes. We're actually going to study some other things such as cylinders, cones, and spheres, but those aren't polyhedra because they have circular or curved shapes, and that makes them not polygons, so they can't be polyhedron. Okay, so the polygons that create the polyhedra are called faces, and they enclose a single region of space, so it's a closed figure. An edge of a polyhedron is a line segment formed by the intersection of two faces. So for example, this right there would be an edge. It joins two faces. And then a vertex, so like right there, so here's an edge, and here's a vertex. It's a point where three or more edges meet. The plural of polyhedron is polyhedra or polyhedrons. You can use either. So those are some of the vocab words that we're going to start with here. And then we have a couple different types of shapes, specifically prisms and pyramids. Okay, so prism has a base shape, and the base is how you're going to name the shape. So, and sometimes you have to rotate them. Sometimes they're turned sideways. And so this would be a pentagonal prism. And then this is a triangular pyramid. And same thing here with the pyramids. You're going to name the pyramids based off of the base shape. And a lot of times the pyramids are easier to identify because they're not, you can rotate them kind of. And I know that's not making a lot of sense here, but so if you take a look at B in this example here, you know that it's got 6 sides, okay, for the base. So this is a, oops, 1 second here. Okay. So that's a hexagonal pyramid. I can't even spell pyramid today. What am I doing here? It's like, what is going on? Pyramid, that's actually a weird word to spell now that I think of it. I don't think I've ever just like spelt the word pyramid while making a video. Pyramid, there. But if we take a look at this prism right here, this is harder to tell, but the base is actually, believe it or not, this guy right here. That's the actual base. So you'd have to kind of rotate that or flip that. So this is a rectangular prism. So sometimes, as I said, they're a little tricky to see. This is a cone. Okay, so tell whether the solid is a polyhedron. So we have yes, yes, no. If it is, name the polyhedron, find the number of faces, vertices, and edges. Okay, faces. Let's start with the prism here. I'm seeing 1, 2, and then 4, so that's 6 faces. Vertices, I'm seeing 4 plus 4, that's 8. And edges, I'm seeing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm seeing 12 edges. Okay, and then the pyramid. All right, faces. There's 1 on the bottom and then 6 triangles, so 7. Faces, let's see, vertices. I'm seeing 1, 2, 3, 4, 5, 6, 7. And then edges, 1, 2, 3, 4, 5, 6, and then 6 more, so that's 12. Now, the reason why that we're doing this is there's a formula that's going to be coming up here, and I'm going to jump right to the formula. It's called Euler's theorem. Okay, it's faces plus vertices equals edges plus 2. It will help you find, if you're given like a large polyhedra with a lot of vertices or a lot of faces or whatever, And sometimes it's easier using this formula than it is to count. Sometimes it's just it's easier to count. So just to verify that, I'm going to go back here. I didn't want to do that. Let's see once. I want to right click on this box and delete this in. Okay, that box is deleted now. Okay, so faces plus vertices equals edges plus 2. So 6 plus 8 equals 12 plus 2. So 14 equals 14. Now it works. So 7 plus 7 is 14. Edges plus 2 is 14. So there you go. And then there's just a couple other sample problems here. This one's no because of this curved shape there. This here we have number 1, we have a square pyramid. And be as specific as you can. Now I got my pyramid spelling down really well. Faces is 5. Vertices, is that the order I wanted to go? Faces, vertices, okay. Faces, 5. Vertices, 5. Edges, 1, 2, 3, 4, 5, 6, 7, 8. And the formula checks out. 5 plus 5 equals 8 plus 2. Now again, this is a problem that looks like it could be a pyramid, but it's definitely not a pyramid. It's a prism, but you have to rotate it over. So this would be a triangular prism. I don't think you'd have to say it is a right triangle, but I don't think you have to say right triangular prism. And then faces is 1, 2, 3, 4, 5 plus vertices 1, 2, 3, 4, 5, 6 equals edges 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. Check the formula. 5 plus 6 equals 9 plus 2. It works out. So it's a way for you to verify if you've done all the counting correctly. Find the number of edges on the frame of this house. Well, this is a weird shape, and I'm going to draw this like this here, because that is, oops. Right, that's what I'm looking for. Okay, so so that's the actual frame of the house. Now what I'm going to do is I'm going to get rid of that there. Okay, that will make it a little bit easier to see. Find the number of edges. Okay, so what I'm seeing is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let's see if I did this right. Faces plus vertices equals edges plus 2. So I'm saying this is 15. So I should have, between faces and vertices, I should have 17. So faces, 1, 2, 3, 4, 5, 6. 6 faces. And then vertices, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Uh-oh. That's 16. So what did I miss? 1. Maybe I counted my edges wrong. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I got 15 edges. Okay, so that means either faces or vertices has to be wrong. So the front, the back. Oh, the bottom. I missed the bottom. See, there you go. Faces is actually 7. And so this was correct, but I was able to verify it using Euler's theorem. So that can be good. And then we have regular polygon, or polyhedron, if all the faces are congruent regular polygons. And then we have convex and concave polygons. Or polyhedron. We've talked about concave and convex. For polygons, now we can just apply this to polyhedra. If any 2 points on a surface can be connected by a segment that lies entirely inside on the polyhedron, if the segment goes outside the polyhedron, then the polyhedron is concave. And so just to kind of give you guys an idea of what that looks like here when we were studying polygons, if I were to extend one of the segments, like one of the sides, and it went inside the triangle, then that would mean it was concave. While this one here, if I extend these sides here, then it doesn't go inside, and so that's going to be similar there. And then we get into this fancy term. These are kind of fun solids. They're called Platonic solids, and this is just kind of more fun information for you guys. These are, in the book actually isn't as specific. The sides, so the faces have to be congruent and regular, and the vertex must have the same number of intersection of faces. The book fails to provide that information there. And so that is actually really specific. But these are the types of Platonic solids. You're going to notice this first one's made out of equilateral triangles. The cube is made out of squares. The regular octahedron is made out of equilateral equiangular triangles. Regular dodecahedron. So do meaning 2, deca meaning 10, dodeca. That's out of regular pentagons. So there you go. There's some fun shapes for you guys. Here's your assignment. It's fairly short. All this section really is vocab. I hope you guys are cool with this. Thank you for tuning in to 12.1.